Hi, this is Shelley Physics episode on magnetic flux. Today's episode brought to you by our school system's new grading policy. Yes, failure is not an option. Oh yeah, think on that one. I love iCall. Okay, so magnetic flux. Well, first I've got a couple magnets here, and everyone knows what happens when north and south sides of magnets come close together, right? They repel. What? South and south. They repel, right? No, they attract. I'm just messing with you. You see, what I've done here is I've turned one of these magnets into an unmagnet. I've repolarized it so that the magnetic fields are swapped. And I do that with this wonderful mystical magical tool. It's one of my favorite tools ever. It's called a magnetizer. You flip this wonderful switch, and I'm going to put try to correct them now. I'm going to put the north side down over here and the south side down over here. There's the south side. Now I'll press this magic button and I'm going to flop the two sides just to make sure we magnetize them on both sides correctly. And now, sure enough, north and south attract. Alright. So what did I do there? I hope you enjoyed that. I hope I had you boggled for a second there. But obviously something was happening inside of these magnets that we can't see with our naked eye. And it all has to do with magnetic flux and magnetism. More about the magnetic nature of iron that makes this up. So I'd like to talk about that today first. Just before we start talking about flux, is what is the nature of magnetism and where does it come from? How is it created in a lot of these magnetic materials that we use on a day-to-day basis? Alright, so a magnet, say a bar magnet here, we usually have a couple of letters written on them, an S, an N for north and south. As you see, this magnet is a dipole. It has two poles to it. As we go through the source of magnetism, we're going to find that magnetic monopoles are impossible. Like if you've got a north, there's always a south. If I break this magnet in half, does that mean I have a north without a south? No, a magnet isn't just about what's marked on it. It's what's making up the inside. What makes up this magnet is atoms. And there's a particular property of iron, cobalt, and nickel atoms that gives them ferromagnetism. And that's the quality I'm talking about today. So if I break this in half, then this part of the north part of the magnet becomes the south, and this part of the south magnet becomes the north. If I break it in half again, same thing happens. There's, inside of a magnet, like this one, there's little tiny NS's, north-souths, that line up. The magnetizer realigns these tiny atomic magnets. And the special property about the iron, nickel, and cobalt atoms comes from their identity as a transition metal. As you add more electrons to the atoms in that transition area, the atoms aren't added to their outer electron energy levels, they're added to the lower ones, and it gives a kind of a stability for this magnetic nature. The source of magnetism, as we're going to explore, comes from the motion of electrons within those atoms. So if you think about an electron with a particular spin, let's see if I have if I have an electron moving in this direction, kind of a clockwise direction, it'll create a downward little pole there. Okay? And likewise, if I have another atom creating that clockwise spin. I hope I have that direction right. Create another downward magnetic field line. So each one of these has, if these represent the little magnetic atom, the spin of the electrons are what's creating those little poles, those north-south poles. As a misnomer, spin when we're talking about atoms is more dealing with the momentum of the electron. But what I mean is the motion of the electron in the atom that is giving it this quality. Okay? So as that electron moves around, we get a north magnetic field going down and a south magnetic field also going down. Okay? And okay, those fields kind of move out and around, sort of like how we've seen electric fields with positive and negative charges. So if you can imagine breaking this magnet in half, these two would become the new north-south. These would become the new north-south. Okay, they have their own magnets created. We take one magnet and turn it into two. I'm not saying go around and smashing magnets. It sounds like a great band title, right? Smashing Magnets? Maybe not. So, just as an illustration, if we do have a magnet and we cut it in half, alright, then it'll just turn into a broken magnet with a south-north side and another broken one here, the south-north side. Alright, so this dipole that was two poles up here become two dipoles. Okay? Dipole. Magnetic dipole. So this one dipole becomes two smaller dipoles. Okay? Just trying to give you some visuals of what's happening here. Alright, so if we consider a couple different types of materials, let's say I've got a bar of copper. I see you, copper. And a bar of iron. Fe iron. Right? And let's say they're non-magnetic. Even the iron has no magnetic field to it. That means if there are some magnetic monopole or tiny magnetic dipoles within copper, there are no magnetic monopoles. The reason copper is not magnetic is because those little tiny dipoles that make up the atoms are all in different configurations. All right, and they could be spinning randomly, but the thing is, copper doesn't have a quality like iron does to make this stable. So for every, let's say, north-south little tiny magnet that's in the west-east orientation, there might be a south-north magnet in that west-east orientation. So what's that going to do overall to this bar of copper? It's going to make it not very magnetic at all. Even if we apply a magnetic field across it, B field, just say we're applying a magnetic field here, these little dipoles, if copper has them, do not align. It's not in copper's nature to do that, based on how the electrons are defined in its structure. However, iron, cobalt, and nickel, if you apply a magnetic field across it, what will happen is the atoms inside will align such that the norths and the souths will rotate and mainly line up. Okay, I didn't draw these perfectly in a column on purpose. Okay, so just showing you that they're mainly norths to the north and souths to the south. over time, magnets can become demagnetized, at least these iron ones can. Um, Earth has a magnetic field, so what's its weak magnetic field going to do to the nature of this magnet if it's sitting on a desk, inside of a drawer for a really long time? It's going to start to realign the little magnetic dipoles within this bar to align with the Earth's magnetic field. Just the stronger the magnetic field that's applied to it, the more those will realign. And that's how in the beginning of the video I had realigned one of these bar magnets so that the North Pole is actually on the south side as it was marked. You can realign those with a strong magnetic field, and that's what the magnetizer does. So that's the difference between the copper and the iron. For the copper, there's nothing useful that happens when you apply a magnetic field across it. Copper is not a magnetic metal. You can put a magnet up to a copper pipe or a copper wire and you're not going to get any attraction or repulsion. Nothing's going to happen. You can rub it. Sometimes you can rub a bar magnet against a paper clip or something like that and magnetize that paper clip. That's not going to happen for a copper wire. All right. So now this presentation is more about magnetic flux, but I did need to touch on that for a really important reason. You might recall a little while ago that electric flux is the electric field that passes through a surface. So if there's a surface in the middle here between this positive charge and this negative charge, and this surface has an area. And by the way, the area has a vector which is perpendicular to that surface, just to remember that, okay? Let's get you on the right page here. So if this is a surface that has an area to it, and that area has a vector, then that vector is perpendicular to the plane of the surface. So there's a positive charge and a negative charge. If we look at the electric field penetrating that surface, then we would find the electric flux by taking the electric field times the area. Now this is a dot product, so it turns into EA, where there's the magnitudes of electric field and area, times the cosine of the angle between them. So each piece of this electric field that's at an angle, plug in the angle there between A and E, and you'd have it. This particular electric field line is in the same direction as E, so as the area, so we would take E times A for that one. So if we just take that entire electric field strength times the area times the cosine of the angle between them, that would be the electric flux. This is the electric flux. So what do you think? What do you suppose magnetic flux is? While I was writing, I hope you had some time to think about it. We're going to use that capital Phi, or Phi, some people call it either one. We'll put a B there. This is going to be magnetic flux. What do you suppose that is? If you guessed B.A, you're absolutely correct. It's that easy. Electric flux, magnetic flux. So we could also write that BA cosine of the angle between them. We'll be really technical with our vector symbols there. We go. Okay, so that's the definition of magnetic flux. So apply that to a magnet now. If I look at it, maybe take a sheet of paper or just think of a surface, a rectangular surface that goes through this magnet, what would be the total flux passing through it? Well, if we put it exactly in the middle, we might have equal amounts of northerly electric field going this way as southerly electric field going this way. If you put it in the middle here, we would have a positive flux from one side to the other. It would be a non-zero flux passing from the north to the south. But what if we surround this magnet passing through the middle with a surface? What would be the sum of all that flux passing through it? I might be getting a little far ahead here, but if we draw a diagram of that magnetic object, that north-south bar magnet, if we take a Gaussian surface, a closed surface, put that up at the top there, closed Gaussian surface, then what would be the sum of all that magnetic flux passing through that surface? Any thought on that? Well, if we surround the north, that just means like north field lines are coming out, right? Hold on. Remember, if we cut this thing off, what do we have in here? We've got two little north-south magnets. So there's also south field lines coming in. It's not just north going out. This is not a monopole like a single positive charge is an electric monopole. All magnets are dipoles. So any field going out of the surface also comes in. Any field going out also comes in. So the sum of all that flux is zero, completely. And to write this in a better way, the closed integral of flux, excuse me, writing that the wrong way. Total flux is equal to the closed integral of B dot dA. I wanted to put it in terms of what that flux is. Okay. And this is Gauss's law for magnetism. Okay. It's not very useful, it's more of an idea, it's more of a concept that we don't have any positive flux going in or out of this closed surface. So, if we back it up just a little bit, this isn't a very useful thing, like I said, it's just a concept. But if we take this further, and I did say back it up and take it further. I'm a little confused here, evidently. So if we move on, what if we've got an example over here? An angled surface. Right? And say this is 45 degrees here. Okay, try to give a little perspective there. There's our area. And let's say we have a magnetic field coming in here. Nice perpendicular lines, so they're all coming at the same angle to the surface. And we'll use a magnetic field of 5 milliteslas. Okay, just as a problem to work out here. Let's say this sheet is like 10 by 5, so we'll say 50 square centimeters. All right. Now 50 square centimeters is 0.005 meters squared. If I divide by 100 and then divide by 100 again, that'll give us the correct conversion there. So that's the area. And we have a B over there. So to solve for the magnetic flux, just as an example, it would be B dot A, which is BA cosine of the angle between them. Okay. So out of that, plugging the values, 5 milliteslas is 5 times 10 to the negative 3. Don't forget your millis there. And we've got the area, 0.005. And the angle, well, you could say 45 degrees because this is a cosine, but let's make it real here. It'll be 90 plus 45. See the angle? We have to, the angle between this and that would be 135 degrees. Okay, so that result turns out to be 5 times 5 is 25, and divided by 10 a few times. Cosine of 135, you get about 1.77 times 10 to the negative 5 Tesla meters squared. And that is the flux value. That's how you figure it. So that is an introduction to magnetic flux, a little bit on Gauss's law for magnetism. I guess I'll end on this point, this note. One more visual here. In terms of Gauss's law, I think I can do this a little bit more. So if you consider a bar magnet, in the field of that bar magnet, got the field lines going out, field lines going into the south. Be oriented something like this. Okay, as a whole. So if you consider several different Gaussian surfaces, let's say this. Got to remember that my electric field diagram here is a bit incomplete, because if I use this as my surface, we've got to cut out the rest of this magnet and consider, hey, there's still a little south in here. And the south isn't just little, like like the word means, but the south is really, really close to this side of our Gaussian surface. So the south portion of the magnetic field here, that'd be going in towards it. Trying to show some field within this magnet. Okay, the field going in is really strong here near this surface. The northerly or outward flowing flux that's hitting this part of the surface from the north side is a nice distance away. So there are a lot of field lines going out this way, but they're weaker, they're further apart. And the field lines closest to this part of the Gaussian surface are very close together. They're very close to the south part of our small dipole that's contained within here. So Gauss's law for magnetism agrees here that the total flux through the surface is still zero. There's a lot of inward flux out here that's equal to the outward flux on the larger portion of the Gaussian surface. Or we could look at the whole thing. Take this as our Gaussian surface. It's easier to look at the whole magnet. The flux, or the flux going out, is equal to all the flux going in. The field lines out equal the number of field lines in. That's a little more visual, a little easier to see there. So I hope that was helpful. This has been Magnetic Flux, brought to you by the people who gave you space and our awesome school system that gave you your Term 3 grade. Oh yeah, failure is not an option.